Surprising fact: the giant magnets in MRI scanners store megajoules of energy in their magnetic fields, enough that engineers design special circuits to release it safely. Today, you'll learn the smaller scale version you'll actually calculate. In this video, you'll learn what an inductor is doing when current changes, how EMF, power, and energy relate, and how to compute energy equals 1/2 LI², plus common mistakes to avoid. Here's the big idea. As current through a coil changes, the magnetic field builds or collapses, and energy flows into or out of that field. When current rises, the inductor stores energy. When current falls, it returns energy to the circuit. Next, the circuit view that explains the signs. The induced voltage, also called EMF, equals -L times the rate of change of current. The minus tells us the inductor's voltage opposes the change in current. That's Lenz's law. The faster the current changes, the larger the voltage. Power is the rate of energy flow. P equals V times I. For an inductor, P equals L times I times dI by dt. If dI by dt is positive, P is greater than 0. The coil absorbs power. If dI by dt is negative, P is less than 0. The coil delivers power back. Let's turn that into stored energy. Start with du by dt equals power. Substitute to get du equals L times I times di. Integrate from 0 to I, and you get energy equals 1/2 LI², the energy stored in the magnetic field at current I. For example, L equals 40 henries, I equals 2 amperes. Energy equals 1/2 LI², 1/2 times 40 times 2 squared, which gives 80 joules. The coil's field holds 80 joules at that current. Careful! Energy doesn't scale linearly with current. Energy is proportional to current squared. If current doubles, energy becomes 4 times larger, not just double. So far, we've covered the opposition sign in epsilon, how power tells the direction of energy flow, and the key result energy equals 1/2 LI². Keep these three linked ideas together. Think you've got it down? Head over to this link for a practice test and join the study streak, or stick around to learn more about the topic. Now, let's try a ramped current case. A 2.5 millihenry inductor ramps from 0 to 3 amperes in 5 milliseconds. The slope, dI by dt, is 3 divided by 0.005, which equals 600 amperes per second. V equals L, dI by dt, gives about 1.5 volts, opposing the rise. What about power and the final stored energy? With about 1.5 volts, power equals V times I and grows as current rises. At mid-ramp, with I about 1.5 amperes, power is about 2.25 watts. After the ramp, the energy stored in the inductor equals 1/2 LI². So 1/2 times 0.0025 henries times 3 squared, which is about 11 millijoules. On the other hand, when current is suddenly interrupted, the inductor tries to keep it flowing, which can create large voltages. That's why we add a flyback diode in circuits. It gives the stored energy a safe path back. Quick error check. Remember the minus in EMF equals -L dI by dt. Energy depends on I². Always keep track of units: henries, joules, volts, amperes. And at high current, inductor cores can saturate. A simple 4-step recipe. First, find the rate of change of current, dI by dt. Second, get the EMF, or voltage, using L times dI by dt and set the correct polarity. Third, if you need it, compute power as voltage times current. Fourth, find the energy stored in the inductor. using 1/2 LI² at the final current. To summarize, inductors fight changes in current, generating an EMF that opposes them. Rising current stores energy as 1/2 LI². Falling current returns that energy to the circuit. Keep an eye on signs, units, and the I² relationship, and you'll master any inductor energy question. Ready to quiz yourself with the content covered in this video? Check out the link in the description where you'll find Quizlet content made just for you.